Hello everyone. This video is part of the introductory lecture on machine learning. In this video we are going to overview the clustering mechanism. Clustering refers to the separation of the available data points into different groupings. So for example, if we have all this data available, so the clustering algorithm is going to make sure that since these points look like each other, they may be belonging to one group, while these points that again are having some sort of relevance with each other are going to belong to another cluster. Separating the data points into these groups or clusters is basically the objective of the clustering algorithm. It's a kind of unsupervised learning. It's unsupervised in the sense that we have given the model with all the data points, but we haven't supervised the learning process, because we are not helping the model to learn what each of these data points represent. So therefore we are presenting the model with heaps of data and allowing the model to find relevance between all the data points, and based on that find the groupings. So how does it work? It basically follows two principles. The first one is to achieve high intra-cluster similarity, and the second one is to achieve low inter-cluster similarity. So based on these two objectives, it will keep on refining itself unless it cannot be improved any further, and that's where the algorithm stops. It may stuck in local optima, and all that we are going to cover in our detailed lecture on clustering, but for now what is sufficient is that how can I separate out all these points into two or any desired number of groups in such a way that all the points that belong to a single group have high intra-cluster similarity, that is, they are more related to each other, and points that belong to different clusters have low intercluster similarity. They are more apart from each other, they are more different from each other. So in case if we use a distance measure in order to identify this similarity between any two points, similarity can be 1 over the distance measure. So whatever the distance measure that we use, the more the distance that we have between two points, the less similar they are, and the shorter distance they have, the more similarity they have with each other. So we'll keep on finding the distances between all the points, and the points having high distance or having low similarity, so we will put them in different clusters, while the points that have shorter distance inversely have high similarity, so we'll put them in the same cluster. The process will repeat until all the points settles into their respective groups, and that's how clustering algorithm works. Now this is a general overview of how clustering or unsupervised learning works. We haven't followed a particular algorithm. There are different algorithms. They all perform this task differently. The internal working or the main phenomena of clustering is the same as we discussed, that we would want a group or a cluster to have points that are more similar with each other, and we would want points in different clusters to be very much different from each other. Clustering is also known as segmentation, sorting, or even some statisticians call it classification. So let's say if a clustering algorithm is given the task to separate out the Simpsons family into two groups. So depending upon the nature of the algorithm that we use, as all algorithms operate differently, so they are going to come up with their own set of clusters. So according to one cluster, maybe all these people are placed in one group and the rest are placed in another group. And if we use a different clustering algorithm, we may come up with another group of clusters which may be different from the algorithm that came up with these two clusters. So all these algorithms are going to present different groupings of users. Unfortunately, since we do not have labels, so it's very hard to identify which groupings is the accurate one. However, we have evaluation mechanisms that help us find which groupings have more compactness as compared to others. So the desired set of clusters would be the one that has instances which are more compact with each other, or as we said earlier, which has high intra-cluster similarity. Since clustering is unsupervised learning, so therefore we cannot label these groups, that what each of these groups represent. In fact, when we label them for a clustering task, we simply call them C1 and C2, and these are basically labels that helps us as a reference to refer to these clusters. However, these labels are not meaningful. Whereas in case of classification, we have meaningful labels and we have definite information that which class each instance belongs to. I'll just repeat the points. The different algorithms that we use for clustering may come up with different groupings of data, which is acceptable because we do not have the actual grouping. We can evaluate all these clustering mechanisms and find out which one is performing better. All these algorithms have their own strengths and weaknesses, and they perform well for different kinds of data. The groupings that we have attained do not have labels, and therefore we just know that all these instances are similar to each other, but we do not know whether they are fruit, whether they are people, or they represent something else. So now the next part is how to find the similarities between 2 points, based on which we may distribute these points into 2 groupings. So for that, we may use any distance measure, and the definition of a distance measure would be that provided any 2 objects or instances O1 and O2, that distance measure gives us a distance of d between the objects O1 and O2. So the distance measure will be provided with the 2 objects, and it's going to give us a numeric value that is the difference or the distance between those 2 objects. We may use different distance mechanisms, and we are going to consider that as a black box. As we can see over here, we do not know how this distance mechanism works, but when it is provided with 2 different species of gorilla, it comes up with a value of 0.23 as the distance between these 2. Now we do not know how that distance measure works. It may have considered the sizes of these 2 species, it may have considered their color and other features that we do not know about. Whatever that distance measure it has given us a numeric value, and that is particularly of interest to us. We want to quantify the difference between any 2 objects so that we can find out which objects are more similar to each other as compared to the others. So once we have this quantified value, now similarity becomes a relative thing. If we have objects O1 and O2 and their similarity is 5, we can only find out if this value is good enough or not when we have access to the similarities of all the other objects. If the other values are between 70 and 105, so now we can say that this is a very good value and these 2 objects are very similar to each other. However, if these values are in a range of 1 to 4, so then we would say that these objects are very much apart from each other. So the first thing that we want from a distance measure is to take 2 objects and give us a number so that we can quantify the difference or similarity between the objects. So as we said earlier, distance is 1 over similarity and similarity is 1 over distance, so we can easily switch between the 2. And secondly, we want to have this similarity between all pairs of objects so that we can relatively find which objects are more closer as compared to the others. So the same way, there may be some other distance measure that is working over here, and that is giving us the difference or the distance between these 2 strings. Now this may be the difference between the number of characters or whatever that distance measure is. It's going to work as a black box again, and we are not interested in how it calculates this value. What we are interested in is that it's giving us a value of 3, and we can find such values for all pairs of strings. Here we have another such distance measure that is giving us the distance between the images of 2 thumb impressions. And again, we have this value, so it's a numeric value that we would want to have, and we do not know how good this value is until we have access to all the other values. So that is the role of the distance measure in order to find the similarity or the distance between 2 objects. Okay, so we said we can use any of the distance measures. I can just provide some of the popularly used distance measures for numerical data. For example, we may have Manhattan distance, where the Manhattan distance between objects O1 and O2 is basically the distance between all the corresponding features of the two objects. So it would be the sum from 1 to n, assuming that the objects have n features, and it will be O1i minus O2i. So we are finding the difference between the feature to feature values of the two objects, taking mod of it and then adding them up, and that would be the total distance between these two objects. So for example, if we have this data where we have three features f1, f2 and f3, and the objects that we have are O1 and O2, and their values are 2, 2, 5, 1, 2, 3. So the Manhattan distance between these two objects would be 2 minus 1 plus 2 minus 2 plus 5 minus 3. So that would be 1 plus 0 plus 2, and it gives us 3. So this is the distance between these two objects. We can convert it into similarity as 1 over 3, which is 0.33 as the similarity between these two objects. So that's how we can quantify the distance between any two objects. The same way, we can make use of the other distance measures also. For example, Euclidean distance, we may have cosine similarity and all that, and we can interchange between distance and similarity. Now, whatever the distance measure that we use, it's expected to obey these properties in order to have a reliable and consistent nature. So one such property is that the distance between A and B should be equal to the distance between B and A. This property is fulfilled by Manhattan distance because we are using these mods. So even if we interchange the positions of these two objects and we convert it into the distance between O2 and O1, the value is going to be the same, because once we take the mod, 5 minus 3 or 3 minus 5 becomes the same. The second rule is the distance between an object with itself must always be 0. So again, it makes sense, and even if we apply this rule to Manhattan, we are going to get 0 as distance for the object O1 or O2 with itself. The third rule is the distance between A and B is equal to 0 if A is equal to B. Now again, it is kind of representation of the second rule, that if 2 points are having distance equal to 0, so basically they are identical. It may happen if we have multiple data points in a data set, and two objects that are having different names may have exact identical values, which would lead to a distance of 0 and would mean that those objects are identical. Finally, the distance between A and B will always be less than or equal to the distance between AC plus BC, which is the rule of triangular inequality. So if we have these 2 points, let's call them A and B, their direct distance will always be less than or equal to the distance when we introduce a third point. So if we have a C over here, so this direct distance will always be less than this, or even have it over here. So in this case, A to C plus C to B is going to be equal to the distance between A and B, but it is never going to be less than this. So these rules must be obeyed by the distance measure that we are going to use for our clustering mechanism. And we have practically seen how Manhattan distance obeys all these rules. All the clustering algorithms that we may use for separating the data points into different clusters may be separated into 2 different categories. So one set of clustering algorithms are called partition clustering algorithms, and the other ones are called hierarchical. Partition clustering algorithms are the ones that would distribute all the data points into the desired number of clusters all in a single turn. So if we have all these data points and we want to have 5 clusters, so it would come up with 5 clusters in the first iteration. In the subsequent iterations, it's going to move the objects around from one cluster to the other based on their similarity to the objects of those points until it settles at the final distribution. So partitional clustering would separate out the data points into the desired number of clusters in the first attempt, and in the following attempts it's going to improve the distribution by switching objects among these clusters. Whereas in case of hierarchical clustering, if we again have all these data points, so the hierarchical clustering mechanism can be of two types, that is agglomerative and divisive. Agglomerative can also be called the bottom-up approach, while divisive may be called the top-down approach. So in case of agglomerative clustering, we assume all these points to be belonging to different clusters. So if we have 200 data points, we are going to have 200 clusters where each object is in a cluster of its own. As it says agglomerative or additive or bottom up, we have all these points at the bottom where we have 200 clusters. Then we would see which objects are more closer to each other, and based on that we would combine some of the points. So in the bottom up we are going to have, let's say, 150 clusters over here. So we'll keep on combining them based on their similarities, and we'll continue the process until we reaches the desired number of clusters, which we said is 5. So we'll keep on merging them until we have 5 clusters, and we'll stop the algorithm over there, and now we have got our desired number of clusters. So it would make the shape of a tree where we have the 5 clusters at the top, and we will have all these branches based on how we combine these clusters. If we don't stop over here, it would keep on merging until we have one cluster as the root of the tree. But that is not going to convey anything meaningful, so therefore we would stop at the desired number of clusters. The divisive or the top-down approach is the exact opposite of this, as it would consider the whole data points to be belonging to one cluster, and then it would see which points are more different from each other, and based on that all the points are going to be separated into 2 clusters. Then it would further distribute or separate the points into more clusters as a top-down approach until we reaches the desired number of clusters, and it's going to stop over there as we have got 5 clusters, and that would be the stopping criterion. So in case of hierarchical clustering, we not only get the desired number of clusters, but we also know how these clusters are related to each other. For example, these 2 clusters, although they are different, but they are more closely related to each other as compared to any cluster from these 3, because they have a common parent above in the tree, which indicates that they are having high similarity as compared to any other cluster. So we can also have some sort of information about the similarities among the clusters, whereas partitional clustering algorithm gives us the desired number of clusters, but we do not know how these clusters are related to each other. So that was an overview of the clustering algorithms that we may consider for unsupervised learning.